Okay, so we have an exam on Wednesday. So today I'll be covering a review for the exam, and I will also be introducing the next project. So we've done project 1. We're moving on to project 2. So project 2 is much more involved, and you will notice there's going to be a decrease in the amount of homework assigned. That is not so that you can spend less time on the course, that is so that you can spend more time on the project. So I'll start with introducing the project, and then we'll move on to the review. So for the project, you're going to see, so I don't know if I posted it or not. If I have, don't fret too much about what's on there yet, because during the lunch hour, I'm going to have to rewrite it because it's still the old project and it needs a little bit of an updating and a little bit of simplification. Right now, it's harder than I want it to be. So I'm using a project from the old semester. But let's start off with the basic element of what this project is going to do. Okay, so you've made your ALU, right? We want to do something with this. We're going to build another component that is very simple, called an accumulator. All this really is a memory bank. It's just going to store some data for us. In fact, all it's going to do is store the output of the ALU. The accumulator then is going to have an output that's back into one input of your ALU, right? Where this is an 8-bit bus, 8 bits, right? Yeah, we're 1 byte. We have 1 byte coming out of your ALU, going into your accumulator. Then the A input is going to continuously monitor the output, right? Where this is just an array of DQ flip-flops. What that's going to do then is take the opcode and make decisions based on A and B, right? So if I want to accumulate additions, so if I want to say add 3 numbers together, my accumulator is going to start at 0, okay? I will then say, let's add B, right? Add A and B. 0 plus B is just B. Then we're going to say add again. B, the old B, plus the new B. We get a new value, C, right? And then we can do that again. Bam. We've just accumulated the addition of 3 numbers. Right? Make sense? If then I wanted to reset it, I would send the opcode command of load, right, which just passes B, and I would put zeros on B. So I say load B, we throw zeros into the accumulator. Okay, so that's the basic building block of what we're doing. This is not very complicated. The complicated part comes in, we need what is called a memory interface. The memory interface is just something that allows us to deal with what is coming in from the opcode and B. There are 2 different things that can happen on the memory interface. Well, there's a couple of different things that can happen on the memory interface. So in the project, when I push that out during the lunch hour, I will submit it. It's going to have a list of operations that it can do to memory port is going to, or the memory interface is going to have some ports. So we've talked about addressable memory, right? Where you're going to need an address. So your memory could either take what we would call the immediate data, which is the next in line. So inside, you're going to have something called the PC, or process counter. A process counter is just going to step through the addresses, essentially, right? We're just going to say, what is the next command in this memory? So we're going to load the memory with a bunch of commands. And the process counter is going to step through those addresses going, what's the next command? Now, the thing that we have to be aware of is that there are fundamentally two different things that can happen. There could be a command where we just do something, or there could be a command and then data. So we might have an 8-byte command followed by 8 bytes of data, or we might have an 8-byte command followed by another 8-byte command. So we have to make that decision of what do we do with the next byte, right? So in the case of let's say hold, we could say, well, let me take the memory command first up. So one of these commands could say something like, I want you to skip to this address in memory, or read from this address in memory, right? So it gets a command that says, read from this address. So the command says, read from, the next byte is more data. Well, in that case, you wouldn't actually, you'd say read from that data and it would pull that data, right? Or it could be load this data. I have data for you, loaded, right? So there would be the command load, the next 8 bytes is the data to be loaded. You do not need to ever handle multiple bytes in a row. It'll always be command, command, or command data. We'll always cycle through one of those two processes. Let me quickly pull this up so that I can remember. So I have not yet finished project 2, because I need to update it. So, again, process counter, there's some, the lab will point out some instructions will change the process counter. And the process counter is just the address that we're stepping through, right? So that's what it means when the lab will say, some commands will change the process counter, it's really changing the address, and then we're going to continue counting up from there. Let's see. Continuing to read or write into memory. So one of the other things we might do is we might take the output of this accumulator and store it in memory, right? So now, something that we have to be aware of is that you're going to write the memory eventually. We're not going to do that yet, but we want to be prepared for when we do. So let's start thinking about what this means. So the ALU, is it combinational or sequential? Combinational, right? No clock. It's just given an input, it spews out an output after some delay. The accumulator, sequential or combinational? Sequential. If it has memory, as sequential. If it has memory, it is therefore sequential. Therefore, it needs a clock. The memory we may implement as clocked or not to clocked. There are multiple ways to do this. If you clock it, which I think might actually be the easier way for you guys to think about the memory, you need to make sure that the change in the accumulator doesn't happen at the exact same time the change in the memory happens. Right? So if I have the clock here, and I update the output of my accumulator at the same time I try and record it in memory, we have a term called a race condition, which there's a race between storing what's on this signal and updating the signal. And we have no way to know which happens first. So instead of having this, a fine way to do this is to call that not clock. Because now I am updating the accumulator on this rising edge, and I am updating the memory here. So update the signal, update the memory. Or you can, instead of not clock, you can make it falling edge trigger, right? Either throw an inverter or throw in falling edge instead of rising edge. Either one of those will be okay. Just be aware that that's something that you're going to have to consider down the line. Let me think if there's anything else there. Clock enables, right? That's something else we just recently talked about. Make sure you implement them correctly, right? Using the mux instead of the gates. Because there will be times that we don't necessarily want to update the process counter on each clock. So if we have this clock ticking along, each rising edge, we're going to update the process counter. We may have a situation where we don't want to update the process counter each clock. So make sure to have a clock enable to your process counter. And then the other thing is, you'll notice on some of the homeworks and some of the labs, every once in a while, you'll see the term ISE. So ISE is the old version. It's the program that came before Movano. It's old and it's not very good. So if I do that, it's just because I missed one case of changing the word ISE to Movano. That's all that is. This we'll talk about occasionally. If I mess up, I will try and remove all references to it. To, what do they call it? Schematic symbols. So in the old versions of the lab, they actually have you create what we call a schematic symbol. So you create a part that looks like this, and then you create a part that looks like this, and then you wire them together with like actual lines. In my experience, I have never encountered anywhere that uses schematics to do their FPGA design, which is when we actually draw things like this, but then our code is matched together with boards, right? So what I like you guys to do in your labs is instead of, well, I won't say instead of, so what I like you to do is, so this is, let's just call it out, right? So I will label my ports out, in, this would be Q, right? We're just gonna call this DQ flip-flop. So then we have Q. And then you can go ahead and name your signals. right? So now this signal is going to be called ALU out. And now when I do my port maps, it's clear to me that my port map of out should have ALU out in it. And my DN port map should have ALU out in it, right? So this is how we use VHDL to connect these blocks. And this is a very important concept within VHDL, in digital hardware in general, is matching the port signal to port, right? And then if we were to do something else with this, it still becomes clear that this ALU out is going to go to 3 different spots, right? So highly recommend starting all of your designs with this, which is we call a block diagram or a schematic diagram. And when you start making the memory, so you're going to get a long list of potential codes that you're going to see from the, there's going to be a table in there that's going to have a long list of commands, right? So what we're really building up is essentially a small slice of a microprocessor. And so it's going to have more commands. These commands are going to have to translate into what are the opcodes, right? So your 8 bits of a command isn't just going to be an opcode. It's going to have more than that. Notice that the memory talks about needing a bidirectional bus. You guys haven't done with this. So the memory interface is going to be an in or an out, right? You might read data in to B, or you might put data out through memory. Now, you can start by creating 2 different groups. But the way you'll ultimately want to do it is you'll say something like, inside of my port, I'll have like, I'll call it memory signal, is going to be of type in out, right? Up until now, we've only used in or only used out. This is going to be in out. Now, this can be a little tricky to deal with because if it's functioning as output, you just write to it. If it's functioning as an input and you're still writing to it, it can break things, right? Because if it's trying to write a 0 and receive a 1, then what is it? We don't know, problematic. So a good way of doing this is, let's build a mux, we'll call it enable. On 1, we'll have memory out. On the other one, we'll just assign Z. Z is high impedance. When we set an output to high Z, it can now function as an input, because it's not asserting anything. And then this is our port. And then, when we're reading, we read from here, essentially. So either we're driving them out or we're just setting Z here and only reading. Make sense? We use constants, right, in this class? You declared constants? If not, quick review. Well, if so, quick review. If not, here you go. So your opcodes, right, are like, how many bits are they? Are they 3 bits or 3? So you might have that. But it's like, what does that mean? So you can actually declare instead of declaring signal like we have, you can actually say something like constant op add. So my operation add is the standard logic vector that gets initialized to 0, 1, 0. And now when I send an opcode, I don't have to write 0 and 0. I send op add. Right? So it makes your code much legible. Instead of having to look at numbers, you get to look at what is your operation actually doing. Make sense? Okay, great. We'll have lab later today and hopefully not face too much confusion. I haven't built this one yet. I've fallen a little bit behind in staying ahead of you. I'm trying to stay ahead of your labs, but I haven't built this one, so there may be a bit of a learning curve. Yes. Yes. So at this moment, I'm going to start project 2 rather than, I think on the schedule is listed as lab 8. I would rather get started on the project because we have everything we need to start this project. The project is more important than the lab in my estimation, so we'll start that and we'll come back around. With the whole COVID thing blowing up, I want to get through the most important stuff first. Make sense? Okay, let me take a drink real quick. I'm going to run out of voice. All right, let's shift gears. Yep, let's shift gears and move on to the review. So exam is Wednesday. The way it's going to work, and this is important, you may come here and take the exam if you would like. You may also take the exam from anywhere you'd like to be. How that's going to work is I'm going to post the exam assignment, and you'll just click on that, download a Word document, and take the exam. If you do that, make sure that you are comfortable changing a Word document into a PDF and uploading that to Canvas. Now, we've uploaded stuff to Canvas, so I know that you all know how to do that. But make sure that you are comfortable with the process, the idea. Because I'm going to I'll give you a Word document and a PDF. You can choose whichever format you download. Now, you may either print this out, write on it handwritten, and then take a picture of it, turn that to a PDF, and then re-upload it. Or you may have a tablet or something like a touchscreen, right? And you'll take it on the tablet and then just save that. Whatever is okay, as long as I end up receiving a clear, clean written, legibly written PDF. Now, I give a lot of points for partial credit as long as you show your work. If you don't show your work, I can't give you partial credit, right? So make sure that you are showing how you're doing things. Let's see. Open book, open notes, open internet, no open people. So no asking strangers on the internet, no asking your friends, no asking your siblings that already went through this program. It's on your guys' honor. I have scores and homework from all of you. If I see something suspicious, I will be unhappy and I may have to start implementing proctoring, which is just annoying for everyone. So just stay honest, because it's really suspicious if you did. If your homeworks don't support your knowledge on the test, right? It's, in general, everybody is bad at cheating, no matter how good you think you are at it, you're terrible. On the homeworks, it's not very important. Mostly, the homeworks are there for you to learn. On the exam, it's not really fair to your classmates or to yourself to try and cheat on the exam, so don't cheat, because we will report you and you can get kicked out of the program, and then you've wasted, what, $6,000 or something. Not worth the risk. Don't think that you have to cheat in order to go get a job. We literally have like 100% job placement in this program. Now, this is not officially university stand. Everything I've been able to find out, anyone that wants a job gets a job, even if you have below 3.0. Like, they're desperate for electrical engineers in industry right now. Some of the numbers that I've seen in estimates, we could have as many as 1,300 engineering positions that go on, that we could fill, that we will not be able to. Over the next 4 years, we'll be undergraduating by over 1,000 engineers. The job market is insane. You guys are in a great place, so when you graduate, you couldn't have picked a better major. Don't cheat and get yourself kicked out of it, is the point. Make sure that you know how to turn the exam in. If your handwriting is bad, be very careful. Write larger, write slower, write clearly. Don't use yellow paper. Some of you do that on homeworks, and yellow paper are very hard to read. Yeah. If it's yellow, don't do it. Don't do it. White. Do white. It's way easier to read. I'm forgiving on the homework. It's not as important on the homework. But on this exam, I want to be very clear so they can clear through. Okay. Into the content that we're going to have. If you screwed up on the K-map part of the last one, go back and review K-maps, because there will be K-maps on this exam. You need to make sure that you can do something like the design process, where if I give you a verbal description of something, you should be able to turn that into a truth table, turn that truth table into a K-map, turn that K-map into a circuit, and turn that circuit into universal gates. Right? Now, we did some of the universal gate stuff in the last time, but I want to make sure that you guys are all clearly aware of the easy way to do it. Right? If I use a K-map and I circle all ones, right? So if I'm using the min terms, then what I end up with, there's no way around this. Right? Is a sum of products, which means I have an output gate of an OR, input gates of an AND. The easiest way to turn these into universal gates is not to do what the book says, because the book is insane. All you have to do is add little bubbles there, right? That means I've inverted those inputs. And if I want to undo an inversion to keep the circuit equivalent, I just create another little bubble, right? But I can just push this guy back to here. Do the same thing on that one. And boom, I have NAND gates. That's it. This is the easiest way to create universal gates from non-universal. If I were to ask you to create a circuit, so this is NAND. If I asked you to create a circuit using NOR gates, what would you do different? Use the max terms, right? Because max terms, the output gate will be AND with OR inputs, right? So that means circle the zeros. And then, when I do the bubbles, I now have NOR gates. Yeah. Yes. Yes. So on min terms, okay. So if I were to take a min term of this, right, and I were to circle these two ones, I look for what doesn't change, right? Well, what doesn't change here? The C does change, so we can ignore that, and we say not A, B, right? And that becomes our term. So we would say F is equal to not A, B, right? But if we're to take the zeros of that same thing, we'll say these were zeros, and this was the term that I circled. Obviously, I can circle 4, so let's make it so that I can't. Right? I'm doing min terms. I identify A and B. First off, there's a couple of fundamental changes. What is that term? And, or. Exactly. I'm not sure. I'll ask you 0, 1. Just be familiar that it exists. I might ask you simple questions about adders and overflow, right? I might ask you to add two binary numbers, right? We did a little bit of that on last exam. We have some more adders. I might just do it for fun because we kept talking about adders. So be aware how to add, especially because they're easy, and I don't want you guys to miss them. Importantly, if we're doing subtraction, and if you have, okay, let me take a brief aside. If you have homeworks that you haven't submitted, turn them in now, because I'm going to go on lunch and I'm going to post all the answers. By now, I mean like right after. I'm going to post all the answers to the homeworks. Once I do that, I can't give you credit for turning in the homeworks. Some people have not turned in a lot of homeworks, and I would hate for you to fail the class just because you're not submitting the homeworks. That being said, let's look at homework number 8, which is part of this this exam. So let's say, and this is what, 3A, just real quick, and you guys can, I'll post these answers and you can go through and make sure you know how to do them, and if I have done something wrong, let me know. Oh shoot. 0, 1, 1, 0, 0. Okay, and I want to add these numbers together, right? Binary addition is, it's easy, it's very simple. I have only a couple of outcomes that can happen, right? I can add 1 zeros, I can add 1 0, or I can add 1 to 1. Now, 1 plus 0, 1. 1 plus 1 is a 0 with a carry. Same thing, 0 with a carry, a 1. Now we get to something interesting, 1, 1, and 1, which is a 1 with the carry. 1 with the carry, 0 with the carry, 0 with the carry. What do we call that term? Overflow. Right? So if I ask you, does it have overflow? Yes, right? Let's do something subtracting. That's a good one. Sure, this one. These were on the last example, right? So this is 5C. Yeah, this is 5C. And it would like us to add these two 2's complement numbers, right? They're 2's complement. So that means because the 1 is here, they're negative, right? Now, there are multiple ways to do this. The way I like to do this is I like to just separate the positives from the negatives, right? Because everything on this side is just a positive number. So when I want to add them, let's just add them. Right? But now, I happen to know that this is a -1 and that's a -1. What happens? Well, I would need to borrow something, potentially, right? Because if I'm trying to -1, -1, I'm getting a negative, I would like to borrow something from there. So I would actually get 0 with a borrow. On the flip side, if, well, this were a 1, right? Then I would have 1 plus 1 is a 0 with a carry, which is positive. This positive 1 cancels out one of these negative ones, but I still end up with -1. I still need to borrow. So I still have a borrow, but I borrow less of it. So I get a 1. If I go even further, then this was a 0. This -1 gets canceled out by the borrowed over +1, and I just get 0 out over. Right? Okay, so the rest of homework 8. Definitely take a look at when you're reviewing. Let's see, what time is it? I will be posting rather, one solution for number 9. Which it's the exact type of problem that I'm going to ask you. I'm going to ask you a question like this, which is you have to start out drawing a truth table and then turn it into, use a K-map, create it into a circuit, and then do something with that circuit, where in this case you actually create individual parts to implement a final circuit, right? Where we follow the design process to go from individual small components, we chain those together and build a little more. So let me pull this up and read you the question. Okay, so it says a magnitude comparator compares two numbers, A and B, and generates output signals A greater than B and A less than B. Use the design process discussed in this chapter to design a 4-bit magnitude comparator. Do not simply subtract B from A. Design a component that takes 1 bit from each from A and B, and also takes signals A less than B, A to 3, or A less than B and A greater than B from the previous state. So what I have provided in the answer solution is something, well, what I haven't posted yet, but I will, is something that's a little bit different than using the A less than B, A greater than B. Because, like many of you are prone to do, I read half the question and then stopped reading and thought I knew what I was doing. So the hint is, the important hint is to design one component that worries about 1 bit at a time, and then chain those together to do multiple bits, right? So the way I did it is, instead of taking the A less than B, A greater than B as the output, I just created something called the propagate, right? So the idea is, if I have two 4-bit numbers, I want to start with the greatest bit, the most significant bit. Because if the most significant bit is larger in one number than the other, it doesn't matter what the rest of the bits are doing, right? So here, in this one, they're equal. So no decision can be made. If here, I notice this one is bigger, I can just ignore the rest of that number. So I decided to create a propagate signal that comes in and just says, does it matter what you do? So if not propagate, nothing. If propagate, make a comparison, right? If I had read the whole question, instead of creating a propagate, I could just create the decision based off of if greater than or less than signals are true, then don't worry about it, right? But as it was, I went ahead and I created a truth table where I had propagate A, B, I had a greater than, less than, and a propagate out, right? And then it turns out that when you do it this way, that if propagate n is 0, these are all zeros. So I can actually write it like that. Oh wait, yes, that's true. Okay. Right? So I'm not propagating, nothing matters. Don't propagate anything to the next one. Done. And that covers 4 rows of this, right? So if 1, then now I can start worrying about the rest of this. Okay. And now here, propagate is 1, so let's ignore it, because we now need to make the decisions on A and B. If A and B are equal, neither of them is greater than or less than the other one, so let's propagate. The next one down the line has to make this decision for us, right? Makes sense for everyone, right? We want to make sure you guys aren't lost and confused on this decision. Then, otherwise, A is less than, right? So this is A less than B. A is less than B. Or A is greater than B. Those will output those two signals. Each of these three columns has to be implemented in their own circuit, right? So propagate, for example, I can then take this is propagate, and we're just going to say A, B, propagate. And then I can ask, all right, so if I have not propagate, well then I have outputs of 0, right? Whereas if I do have propagate and not AB or AB, that's my propagate. And then I can turn this into an equation, right, by circling it, which is this one is, and this is P out, this is P in. And I have not A, not B, P, or A, B, P, right? And then I can easily turn that into a circuit. Now, once I have that, I could draw the components, right? So I'm going to skip the part where I draw the circuit and show what goes inside the component. That component, right? I have inputs A, B, and P in, and outputs greater than, less than, and P out. And now, if I take a second one of those, I'm trying to build a 4-bit, so I start at 3, right? If I look at A and B of those, if A is greater than B, this will go high. If B is greater than A, that will go high. This initial propagate has to be fixed to 1, because I have to make that first decision. And now, if A is greater than B, I get this, and P out goes to 0. P in is 0, so nothing happens on down the chain, right? P out is 0, P in is 0, that means P out must be 0. But this means now I have 1, 2, 3, 4 different greater than or less than signals. I need to combine those for one decision. What is the right gate to make that combination work? So say that I have these two numbers, where this is A and this is B. Not XOR. So I have two outputs that I want. So this is greater or less than local. And then I'm going to have down here 2 ports where I have a greater than and less than. right? I have a single port that I have multiple inputs to. So what is that decision? An OR gate. Right? And now we know, because we designed it, that only one of these greater than or less than will ever be true. And now if this either one of those is greater will be true. If either one of less than is true, less than is true. They can't both be true because we designed it that way. Right? We're done. The design process makes sense for everyone. This is that idea, this concept is one of the most important takeaways from this class. So I can say with a high degree of confidence that you will have a question that asks you to design one module that can cascade into more. I just had a message that said it doesn't look like my microphone is working, but the audio changes like it's working. So hopefully this works, otherwise I have more work to have. Okay, so I didn't assign homework 9, is that correct? Then homework 10 is all the HDL. Homework 11, yes, gate stuff and some multiplexer stuff. So the main idea of the multiplexer that I think some people are struggling with let's say, and we've asked this multiple times, right? If I have only 2-to-1 muxes and I need a 4-to-1 mux, I need to stick them together. Right? I have 4 inputs, 1 output. Each of these have a select signal. If I have 4 inputs, that means I need, right, 4 inputs, I have 2 to the n outputs, I need n inputs. Sorry. Right, so 4 inputs, 2 to the n. Call them selects. Right? So I have 4, 2 to the 2 inputs, but I need 2 select signals. Where in this does select 0 go? The first 2. So the first bit says it's going to either be this one or that one if it's 0, right? Then this one will choose top or bottom for us. So now 0, 0 is 0, 0. 0, 1 is 0, 1. Right? Now we can, using this architecture, we can access any of our inputs based on the output based on the slice. So there is in homework 12. So for the review, we've only got like 15 minutes left. So I will try and keep this as on point as possible. So make sure to go to your homeworks after I post these and make sure that you understood them. I will not post quite all of the answers because some of them were obvious, so to speak, or just Googleable, or in some cases they just weren't important. Like literally on homework 12, there are problems 3 and 4, and on the solution I literally skipped it because it won't be on the exam, so don't worry about it. So the point of these are to help you prep for the exam. Okay. But number 5 on homework 12 is really interesting because it asks you to create a shifter using nothing but 4-to-1 multiplexers. So I'm not going to post the code to that because that's not really what's the important part, because I believe that you can write the code once you have the architecture of the circuit. So let's start with the architecture. So the challenge is I needed to use nothing but 4-to-1 muxes and shift, right? So let's do this for 4 bits. That means I have 4 inputs and 4 outputs. Let's start by worrying about the first output. I have mux. I have the output. Let's call the output F. This is a 4-to-1 mux. So I have a 2-bit select, right? This thing could be built out of what I just earlier drew up with the muxes, but let's not worry about the internal workings. And give it 4 inputs. Now we can go ahead and say, let's make select. Instead be select, let's call it shift. And it is now the amount I'm going to shift by. So this is the lowest order bit. If I don't shift at all, what should F0 be? If my shift is 0. Yes, it should stay the same what our input is. So I'll call that I at 0. So I have input vector I, output vector F. If the shift is 0, F0 is I0. No shift has happened. Let's continue on. If my shift is 1, and I want to fill the least significant bit with zeros, what is F at 0 if shift is 1? So I want to shift left and fill with zeros. This is I at 0. And F at 0 should be, right? So F at 0 should fill with zeros. Okay. Right? If I shift by 2, I'm still going to fill with zeros. by 3, still going to fill in the zeros. So if I do anything other than don't shift, then I get a 0. If I don't shift, I just stay when it was. So now I have this block. Where I've given an input and I give an output shifted. Right? Well, let's real quick nothing changes if I don't shift. Take I at 1. What happens if I shift by 1? Right? And I just repeat that, getting less and less zeros and more of the inputs. Let's take it a step further. What happens if I want to barrel shift, meaning it wraps around? So my barrel shift gets 1 barrel shift left, does that. Yeah, so let's do that for this one. If I shift by 1, what do I get? Exactly, I at 3. If I shift by 2, I at 2. Right? And now I just wrap those around on down the chain. Okay, other topics. I will ask you, I promise I will ask you questions about VHDL. I will show you VHDL code and ask you what is wrong with this code. So I want you to understand the idea of what I was drawing up earlier with the ALU. If I give you a component and it has these ports, and I show you that these ports are supposed to be that port and ask you, is these actually? I want you to have the idea that if I use for standard, so for bits, right, I do that. For vectors, I do that, right? And I can't do something like on a signal that is an integer and ask if they're equal, right? So I can't say, is this standard logic vector equal to this integer? Because that's nonsense, right? Apples to oranges. So I would have to do some sort of conversion. So I want you to know that. I want you to know this is asking the question, are they equal? And this is making an assignment, right? If I give you VHDL code for a D flip-flop, but change the names around, so instead it's like Flipper and Donald Duck as the variable names, can you still identify what it's doing? Do you still recognize it as a D flip-flop? Do you still recognize it as a Mux, a JK flip-flop, and so on? Can you read code, identify what it's doing, and relate it to these devices that we've used? Do you know the difference between sequential and combinational logic? Right? The sequential logic will be fairly simple if I ask you questions on those, right? Because we're new to sequential logic. There will be some questions about it, but they'll be lighter on the load. Have we done any homeworks that have sequential logic in them yet? I don't think so either, so it'll be more of the conceptual stuff. I can get away with asking it because it's open note, open book, open internet, right? So there will be questions about flip-flops, just the conceptual level mostly, and the VHDL kind of code level. There will be questions about muxes, there will be questions about shifters, there will be questions about adders, there might be a question about a subtractor, There'll be questions about the HDL declarations and signals, and I will probably ask you to handwrite just a little bit of VHDL to show that you have some idea. And there will definitely be questions on the design process, right? That's chapter 8. Make sure that I can give you a verbal description and you can give me back a circuit. There will likely be some form of question about one of the labs we have done since the last exam. One or two of the labs. Which, if you recall, is lots of VHDL. Do you have okay. Do you guys have any questions on any of the content? What? You can't open it. Why not? What does it say? I don't know. I don't know yet. I have not written it. I will be writing it tomorrow. It will be designed such that you can finish it in an hour and 15 minutes. And then you will have 15 minutes to submit it. The way that will work for in-person people is I will just let you keep going after the hour and 15, and I will watch those submitting it online. And essentially, once half of them have submitted it from online, then I will make you guys all turn it in. So that you all get basically the same amount of time. Because I know, the way it works out is I know some students are doing it online will try and use those extra 15 minutes to try and get it more done. That's a high risk scenario because if you don't get it turned in, you get nothing. So I do the median, like once half of them have done it, turn it in, then I will have everyone turn it in. Because by that point, almost everybody is at least working on trying to turn it in. And if they aren't, they're really enjoying it. So it should be finishable in an hour and 15. If it's not, I sometimes make mistakes and the exam will run a little bit long because I haven't written that many exams in my life. If it runs long, my recommendation to you, if you look at it and you ever run into a problem that you're like, I have no idea how to do this, just skip that part and go get the points that you know how to get. Because if it's hard for you, it's probably hard for others. If it ends up hard for everyone, it'll get curved. I don't think I had the curve the last exam because it ended up being the right length, about the right difficulty, and everything was nice. For my 3610 courses, I have consistently curved it about 10% upwards. I will not ever curve it downwards. I'm never going to curve to make things worse for you, as some prestigious universities like to do. Yeah. So if you're struggling on something, skip it. Go get the points that you know how to get. If you see true falses and you don't know, you can leave it for a little while, but always go back and circle something and take it. Because I don't write my true falses as lose points for getting them wrong. I will maybe create like a matching question, like match these circuits to whether they're combinational or sequential, and then those ones I might mark down if you get guess wrong. So you should only you get -1 if you just don't fill it in, and -2 if you guess wrong. So with the true falses, I won't do that one ever. So go ahead and take your guesses at those because not circling them is just terrible. So you got 50-50 of getting the right answer anyways. So there will be true false, there might be matching, there will be questions about combinational or sequential, there will be questions about VHDL, there will be questions asking about write combinational logic to achieve X, right? probably anything about write a process to do X, because we haven't really done that outside of the lab. Right? We don't have one lab, I think, now that's done that. Yeah, hopefully this is not too big of a challenge. I hope you all do as well as you did last time. On average, I'm really quite happy with it. My most important takeaway, the last thing I'm going to leave with you, get your homework turned in, guys. I don't want to see you fail because you're just falling behind. If your life has imploded and everything is terrible and you need to figure out how to catch up, come talk to me. I do want to see all of you succeed. I want to see you all be miserable in my 3610 class in the fall. Something I will say, you are likely to hear horror stories about my 3610 class and how difficult it is. It is now, as of right now, the most difficult class in the program, according to some students. That being said, it will get easier. I'm making the next year will not be as hard as it was this year. It was incidental. Despite their complaining, they're all doing very well. Their curve looks almost exactly identical to your guys' curve, so don't let their whining complain. And the other is, it applies directly to industry. If you take this class and then that class, and you go out, the interview questions you get for digital design class will feel like you were in that class. Like, it is one-to-one mapping of what do you do in industry and what you do in that class. It's a great class. You should take it. It's that or power, and power doesn't pay money, so you don't want to do that. That's the time. We're out. Go ahead, start reviewing. I'll post these over my lunch break. Get your homework submitted. Shoot me any questions as you review them if you run into issues or think I solved something wrong. Because I did all of your guys' homeworks that you did over the last third of the semester in 2 hours, so it's possible I made mistakes.